Okay, my name is Jong Park. I'm with Department of Military Digital Convergence. And welcome to the Signals and Systems class. In the previous lecture, we have finished continuous time Fourier series and Fourier transform. We have gone through the properties of the Fourier transform for the continuous time case. So we have observed that they have a symmetry property where the magnitude is an even function. It's symmetric in terms of the y-axis, and the phase function is an odd function, which is symmetric with respect to the origin. And also, the time scaling becomes the frequency scaling in the frequency domain, and we did the proof of it. And also, I introduced the word duality. So the basic thing about duality is like if you conduct the Fourier transform twice, and then you get the original function, which is represented by this small x. Of course, you have to multiply by 2 pi, and you have to reverse the omega axis. However, the important thing is that you get the original function. And we are already familiar with the first one, so I just did the proof for the second one by exchanging the parameters like this and like this. And we started with the even function, therefore you cannot witness the this minus omega here. But if you do this duality, if you do this Fourier transform twice with like normal function, then you will observe that x of minus omega in this result. Also, we covered Parseval's relation without proof. So it's about like total energy in time domain equals the total energy in the frequency domain. It's proportional because I have to do this multiplication of 1 over 2 pi. And I introduced time shifting, differentiation, integration, linearity, and convolution, and it's your job to prove these properties. I haven't gone through the details for this. I just listed the fact of each property and not going through the whole proof. And I told you specifically to prove it because it can be on your test or your homework. Okay? And I made an emphasis on this convolution because it's a mathematical and conceptual basis for the filtering, which is a major, which is very big field, like for the control theory or for like integrating or like constructing a framework for some physical systems. And you have to perform the convolution, which I introduced in chapter 3, to process through the LTI system in the time domain. However, this involves very annoying process because you have to do this integration from minus infinity to plus infinity. However, if you just transform from the time domain to the frequency domain just by this Fourier transform, then this convolution becomes the multiplication. So it becomes very easy for you to do this computation, which represents processing through the LTI system. And this h of omega is called frequency response, and of course this is a Fourier transform version of the impulse response. So for filter, we notified this ideal low-pass filter, which is very famous, and the differentiator is kind of the high-pass filter. However, it's non-ideal high-pass filter. Also, the modulation is about the reverse step of the convolution, and thanks to the duality, you have this additional property. And we covered the usage of this Fourier transform in solving the differential equation. And that was the end of the previous chapter. And our chapter today is number 8, which is about discrete time Fourier transform. As I have told you before, many things are similar to the continuous time case. Therefore, we will start by reviewing what we have done for this Fourier series and Fourier transform. So the basic motivation that we're doing right now is to decompose this input as a linear combination. So if I have some randomly generated complicated input signal x, you will decompose them into like a1 pi 1 plus a2 phi 2 plus so many things to represent this x. And if you process through this system, then you will get this output because of this property of linearity. And we need to choose this basic input, pi 1, pi 2, pi k, or pi kn, because we are with this discrete time case. With these two factors, so broad class of signal x should be constructed by this basic signal, because that's because we are building this input x out of this basic inputs, right? With this linear combination relationship. Also, these basic inputs should be easy to compute for their response, to analyze their property and their result. So the first basic signal we have chosen was a delayed impulse, and it ended up with the concept of the convolution representation, remember? And now our second basic signal was the complex exponential, which led us to this Fourier series and Fourier transform. So this second basic signal was in the form of exponential for the continuous time. So this basic input was e to the j omega k t. And omega k was a fundamental frequency, remember? And the reason why we have adopted this form is because of this eigenfunction property. So if I treat this form of exponential as an input for the LTI system, and you will get the same exponential with the same frequency. This is the key part, with the multiplication of something which is a function of omega k. you will get this so this integration is a function of omega k, right? Because this tau here vanishes after the completion of this integration. So only change in complex amplitude. Even though you process through this LTI system, you get the original function, original input, and multiplied by the amplitude. So there is only a change in complex amplitude, right? And here, this whole thing, we defined it as large H of omega k, and we called it a frequency response, remember? We did it in the last lecture. And of course we can define this H of omega k by saying that it is a Fourier transform of system's impulse response, right? We all know what impulse response is. An impulse response was represented by the small h of t, remember? So large H refers to this Fourier transform of small h. And decomposing the input signal as the combination of these complex exponential resulted in the Fourier series representation and Fourier transform representation. So decomposing signal as linear combination of these complex exponentials resulted in the theory of Fourier series representation. And moreover, Fourier transform representation. So thanks to this eigenfunction property, when you're trying to obtain the response, you only have to obtain this frequency response and multiply to the original input. Okay? So thanks to this eigenfunction property, you only need to obtain this frequency response H of omega k and multiply it to your input, which is e to the j omega kt. I would say calculate. Excuse me. multiply the t to this original input for obtaining the response. So this was the review for our continuous time case for the Fourier series and Fourier transform, and also the basic motivations. And now we're gonna do for the discrete time case. And as I have told you before, many things will be similar to the things that we have done for continuous time. Nonetheless, there are different parts. Obviously, there will be different parts between this continuous time and discrete time. So I want you to focus on those different factors. Okay? Okay, so I think we can start now. So basic signal in discrete time can be expressed as follows. So we will have phi k with a square bracket. Remember, we use this square bracket to represent this discrete time. And this equals e to the j large omega k times n. So t becomes n for this discrete time, and omega k becomes large omega k, so the capital omega for this basic signal in discrete time. So there exists the same eigenfunction property for this discrete time. Which is, if you insert this e to the j large omega k n into the LTI system, then you get the same exponential function, and you have to multiply it by the summation. So it was the integration for the continuous time. However, it becomes this summation. So e to the j large omega k n times the summation from minus infinity to infinity, where you have h of r. So r is a parameter for this, is a temporary parameter for this summation, times minus j omega k r. Now this is a So this is like the same thing for this frequency response in continuous time, okay? Practically it's a very similar form if you convert this integration into this summation. So this is also called of course, this is also called this frequency response, just in the discrete time. And for those of who want to get the definition of it, I will just say discrete time version of the Fourier transform of this impulse response for the LTI system. Okay, so it's practically the same thing. However, it's in discrete time now. So as we have done for the continuous time, we will start with the periodic signal. Remember? We will start with the periodic signal, and then we will extend to the non-periodic signal, which in fact was the generalization. Okay? So obviously the periodic signal will lead to Fourier series. So now it's a now it's a discrete time case. And it should start with a periodic signal. So this discrete time x of n is assumed to be periodic signal. And remember that this period large n from our introduction, this was the smallest positive integer, remember, for this discrete time. So it's the smallest positive integer for this discrete time. I forgot to put C here. And what was the fundamental frequency for this x of n? We denoted this fundamental frequency as large omega 0, remember, and this was 2 pi over large n, remember? So we had this relationship between the fundamental frequency and the period, as their multiplication should be 2 pi. And with the same idea from this continuous time, we will consider this we will consider this fundamental frequency as well as harmonically related frequencies, right? So with this, not only this fundamental frequency, but harmonically related frequency will be considered to construct this x of n. So we can have the expression of this harmonically related frequency as this e to the j k omega 0 n, large omega 0 n, excuse me. So by varying this k, of course this should be an integer, right? So by varying this k, we can generate these harmonically related exponentials for this integration. So now we can construct this x of n, this periodic signal x of n, by summing this harmonically related exponentials with the appropriate coefficient, as we did in the continuous time. Because all we want to do right now is to represent this x of n by this linear combination of this basic signal, and that basic signal is not only fundamental frequency but also the exponential with the harmonically related frequencies. Okay? Therefore, we can express x of n by this summation of the parameter k, where we have to multiply by the appropriate coefficient, which we represented that coefficient as ak in this continuous time, so we will adopt the same notation, multiplied by e to the j k large omega 0 n. So this summation is the function of k, and if you resolve this summation, then it becomes the function of n, right? Like here. So this represents So this equation represents the linear combination of this e to the jk large omega 0 n. And I will call this equation as 8-1 because we are in chapter 8. Now, there is a special property about this discrete time. So when we first studied about this sinusoidal wave, I think this is it. Like, for the continuous time, if you have different value of omega 0, then it's distinct signals, which means it's just a different signal. However, for this discrete time, if you have values of this omega 0, which is fundamental frequency, separated by 2 pi, then they become these identical signals, and we did this proof for it. So because of this property, so this was the property for continuous time, and for the discrete time, we can obtain identical signals for values of large omega 0, which is the fundamental frequency, separated by 2 times pi. So with the above property of the discrete time, I can equate e to the jk omega 0 n with e to the j k plus large n omega 0 n. And the reason is that first you have to note that this e to the j k plus n times this can be treated as the sinusoidal signals due to this Euler's relation that we always used. So this becomes cosine of k plus n times omega 0 times n plus j sine of the same thing. Remember that this was this Euler's relation, right? You can look into any books and have this relationship. So if you look at this cosine part, and with the distributive law, you can say that I have cosine of k omega 0 n plus large n omega 0 n. And I can treat this n times omega 0 by 2 pi because of this relationship between the period and the fundamental frequency. So if you just carry this large n to the left-hand side, then you will get this equation. And I can witness this. I can treat this n times omega 0 as 2 pi like this. So this cosine becomes cosine of k, become the same thing plus 2 pi n. And since we know that this n is an integer because it's a discrete time case, therefore we can just, so it's an integer times 2 pi, so this contributes to nothing new, right? So I can say that this is k, this is cosine of k omega 0 n. And I can do the same thing for sine, right? But I'm not going to repeat that because it's just waste of the page and our time. So if you do the same thing for the cosine and the sine, then I will have cosine of k omega 0 n plus j times sine of k omega 0 n, which is exponential of jk omega 0 n. So with this property that I can form this relationship. So the meaning of this equation is that, for example, at k equals 0, for example, and at k equals large n, you will have same complex exponential. Right? And if I change this to 1, and to become the same complex exponential, this should be n plus 1. You get it? Therefore, I want to say that like in the continuous time, we did this integration from minus infinity to plus infinity. However, in discrete time, because of this property, you don't have to do the summation for like infinite times. You only need to do for just one period, because after that, the complex exponential repeats itself, right? Just like it's a periodic, it's just like it acts like a periodic signal. So the range of k of this summation for equation 8-1 if it starts with 0, then you can stop at when? You can stop at n minus 1. Also, if you try to start the summation k from 1, then you should stop at large n, which is the period of this periodic exponential. And of course, you can start with 2. It's your choice, but you have to finish at n plus 1. So, like, how many numbers do you need for this equation 8-1 for its summation? You should have large n of them. So what I'm trying to say is, like, it does not matter like what interval you consider, as long as you stick to just one period. So the number of it is n. So, I mean, like, it does not matter where you start this summation. You can start from 0, you can start from 1, you can even start from like 5 or n divided by 2. If it's integer, that's okay. However, you have to stick to one period whose number is the number of summation, the number of index for the summation should be large n. Okay? So, I can say that this equation, now we know that we don't have to do the summation for like infinite times as we did for this continuous time. So, now we can say that our expression of the basic signal for this discrete time can be formulated as the summation for only one period. And inside the summation, we have ak times this complex exponential. So our new notation here, where we have this special bracket, the definition of this bracket means you are going to do the summation over just one period. Okay? So this is the point of the Fourier series of the discrete time case. So we have new notation, which is about ranging over just one period. And this is possible because of this property for the discrete time. Okay? I mean, you don't have to do this summation for the infinite number of time because it results in the same complex exponential. And that's the reason why we can just do the summation for one period, and it does not matter where you start as long as you keep this one period. Okay? Now, how do you determine this AK? So that's like the main thing that we did for the continuous time, and this will lead to the analysis equation for the Fourier series. So our next question is that how do we determine that? How do we determine the coefficient AK? So contrary to continuous time, for our discrete time case, we have a closed form solution because we do the summation for just one period. So we have a closed form solution for the discrete time case because we are just do the summation for the one period. Okay, so recall that we have, I think I might as well copy this, but you guys don't have to because I'm just copying this because I have no room for the previous page. Okay, so what happens if I put this n as 0? Then I will have x of 0, and I have to do the summation for one period. However, I have this n as 0, so we have just AK. What happens if I put 1 for n? Then I still have to do this summation for one period. However, I have AK times e to the jk omega 0, right? if I have this if I put 2 for n, then I will get e to the j k omega 0, because n should be 2. I'm not sure I have to make this parenthesis, so I will just say I will start with j times 2 k omega 0, I will say. So I can do this for, since I started with 0, I should end at n minus 1, not n, okay? So, because you need to have just large n of this period, because that's the number of period for the discrete time. So I ended up at n minus 1, and I will have the right hand side look like this for this n minus 1. Okay. So how many equations do I have? I have n linear equations. I have n linear equations for how many unknowns? So this is like solving this linear equation. So it's like an algebra now. So I have n linear equations for how many unknowns? Our unknown is ak, and how many unknowns are there? If you start with 0, you have to end up at n minus 1. So you have n unknowns. So with n equations for n unknowns, it's a perfect balance, and you can solve it to obtain these unknowns. So if you solve it, I'm not gonna go through the detailed procedure. However, you will, if you do the math, if you do the linear algebra to solve this equation, then you will end up getting ak as 1 over n summation of one period as x of n e to the minus jk omega 0 n. So please note that this k becomes n now, because you should have the function of k for this coefficient. And please recall that you have this equation. Now you have this analysis equation and the synthesis equation for discrete time case. So I skipped the part to solve this equation, but if you solve it, and you can solve it because you have n equations for n unknowns, then you will get this equation. And that solution is the analysis equation for discrete time case. And the former, the linear combination of this exponential is obviously a synthesis equation for the discrete time case. Okay, to compare with this continuous time, I will write down this analysis equation and synthesis equation as well. So versus the continuous time. we had this analysis equation of AK equals 1 over T0, remember? dt. And we had this x of t as the summation from minus infinity to plus infinity, where you have to have ak times j to the k omega t. So if you compare these two, if you compare the analysis equation for discrete time and continuous time, then we notify that you have this summation for discrete time. However, you have this integration for continuous time. So that's the difference. And if you compare this synthesis equation for discrete time with continuous time, then the main difference is that for the continuous time you need infinite number of summations. However, for the discrete time you only need the summation for one period. So that's the key difference between this continuous time and the discrete time. So the summation is same. You have summation for both sides here. However, you can restrict that summation for just one period for the discrete time case. So, as I have pointed out just before, that you have the same value when k is 0 and k is large n. Also, you will have the same value for k being 1 and n plus 1. So it's periodic. So if you carefully examine this analysis equation, then you will find out that this AK is also periodic for the discrete time. Okay, so I mean, so xn is periodic, right? With respect to n, because we are only dealing with this periodic signal, because we have restricted the signal to this periodic for the Fourier series case, Fourier series case, and then we will of course extend to non-periodic signals. However, since we're dealing with this periodic signal, this xn is periodic in terms of n, right? And also this basic signal, complex exponential, is also periodic with respect to n. And these are so true for both continuous time and discrete time, because we set up the whole thing about this Fourier series like this. Okay, so we already set up the the environment to derive this Fourier series for the periodic signal, and of course this fundamental building blocks, which is a basic signal, they are also periodic with respect to the timeline. However, as I have told you that we have the same value for this complex exponential because of this discrete time property. This e to the j k omega 0 n is also periodic. So it's the same thing, but I'm rewriting again, and it's also periodic with respect to k. But now this property only belongs to the discrete time case. And because of this, this ak is also periodic. So this is the property that you have not witnessed in continuous time. So this is also periodic with respect to k. So you have to see the difference between n and k. So these two are only for what? Only for discrete time. Okay? Yeah. So I really wanted to point that out. And now I think we can move on to some examples. Okay? So the first example is the discrete time signal where we have 1 plus sine sigma 0 n plus 3 times cosine sigma 0 n plus cosine of 2 omega 0 n plus 2 pi. So if we insert this function into this value, and we can adopt this ak. If you do that, then you will have this result. So I'm not going to do the calculation for this example, but I really wanted to point out that this AK, okay, this AK is a periodic signal itself because of this statement. AK is periodic in K. This only happens in discrete time case. We never witness this kind of property when handling the continuous time case. So if you can see from the real value of AK, imaginary value of AK, and even in the polar form, the phase or the magnitude, you can see it's periodic, right? Also this, and also this. So you can see that coefficient AK repeats himself. So the main point I would like to express for this example is that this coefficient AK is periodic. I would like to proceed with the second example, and this is called a square wave. So xn is 1 when its absolute value is smaller than or equal to large N, and 0 otherwise. And if I may draw this, no, I will just import this signal. No, I think I haven't uploaded this in the iPad, so I think I will draw it. So that's no big deal. So the square wave looks like this for the discrete time. So it looks like I need to put this subscribe to distinguish this n from the period n. Therefore, I have a 0 here if I have n1 here and minus n1 here, and you will have ones all the way up to n1. And since it has to be a periodic signal, if you have n here, then you will have the ones also here. Okay? And you have zeros for the others. And of course, if you have like minus n here, then you will have ones here. Okay? So this kind of square wave, I would like to do the calculation to obtain this coefficient for the Fourier series. Okay, so let's begin. I'm starting with the definition of our discrete time case. So 1 over n times the summation for one period, right? The summation for one period with xn e to the minus j k omega 0 n. Okay, I think I got that right. And you can see in the figure that I really want to. Okay, so the period, if it starts from the 0, then it will end at n minus 1. But I don't want to do that. I mean, I can select these for one period. However, it does not matter if I do it with these, right? So I will set n as minus n1 all the way up to plus n1. It does not matter, right? Because it does not matter where it starts as long as you summation, if you do the summation over one period. So this equation becomes 1 over n, n being n from minus n1 to n1. And if you, what's the value for xn? It's 1, right? So I get 1 times e to the minus jk omega 0 n. And this means that this summation is a finite summation now, okay? It's not infinitely long summation. It's a finite summation. So I can write down this by putting this summation values, orders for the small n. So it starts with e to the minus jk omega 0 minus n1 all the way up to e to the minus jk omega 0 n1, right? And I'm gonna use the formula that I introduced earlier, which is summation from k being 0 to r, alpha times b to the k equals 1 minus beta minus 1 minus beta to the r plus 1 times alpha. So alpha has nothing to do with this summation, so we can just, come to the, you can like get out of this summation. And let's figure out what alpha, what beta, and what r is for this our case. Okay, so I'm just going to deal with this bracket here, the inside the parenthesis. So if I compare that, since we're starting with 0 for k, the first value should be alpha itself, right? So alpha should be e to the jk omega 0 large n. And what is beta? Like if you now the next term is minus n1 plus 1. So if you treat n as minus n1 plus 1, then it means you're multiplying it to e to the minus jk omega 0 compared to the first one. So this beta here becomes e to the minus jk omega 0. Please correct me if I did something wrong, okay, by the email. And what is r? R is the number of the summation, the terms inside the summation, and you have how many? You have 2 times n1 plus 1, so don't forget for the 0. However, since we're starting from 0, r should be 2 times n1 for the count to be 2 times n1 plus 1, right? So this is 2 times n1. So we have found the values for this alpha, beta, and r. So we can just rewrite this summation with this formula. So alpha comes first. I will deal with alpha first. So e to the jk, the n, times 1 minus e to the minus jk omega 0, 1 minus e to the minus jk omega 0 with this r plus 1. So I will have 2 and 1 plus 1, like this. Okay, so this equation becomes we will have the same denominator. However, I will modify the numerator part to deal with this alpha here. So 1 becomes e to the jk omega 0 and 1, and minus stands still, and this one, if you like use the distributive law, you will have minus 2 and 1 minus 1, and you have plus n1. So this minus 2n1 plus n1 becomes minus 1. So this will be like e to the jk omega 0 minus n1 minus 1. Okay, are you following? Okay, so this may be the answer, but I would like to express this solution with this sinusoidal wave for us to be more feel what it looks like. I mean, I know there's no problem with this formulation. However, j being on the top of the exponential term, we cannot see this. We cannot actually see what it is. Of course, some smart people can do, but I can't. So I would like to use this Euler's relation to express this in the sinusoidal wave. However, before that, I want to do the multiplication to make it prettier. So I will multiply both for numerator and denominator by this e to the 1/2 of jk omega 0. So please follow me why I'm doing this. Okay, so I think I'm moving to the next page, but you can still write down on the bottom of the recent equation. So if I multiply both sides by e to the 1/2 of jk omega 0, then this equation becomes minus this becomes 1/2 because you had one of them. You had minus one of them, excuse me. You have minus 1, but you're going to add 0.5, so you'll have minus 0.5, which is minus 1/2. And for the numerator, you will have e to the jk omega 0 with n1 plus 1/2 minus e to the minus jk omega 0 with n1 plus 1/2. I just moved this minus n1 to the front. Okay, so what happens to the denominator first? So I'm gonna do the denominator first, and if I use this Euler's relation, then I will have cosine of k omega 0 over 2 plus j times sine of k omega 0 over 2, and minus you will have cosine of the same thing because cosine is an even function and minus sign cannot do anything. However, with the sine function is an odd function, so the minus inside the sign can come up in front of the sign. Remember that? So you can't just miss the details. And then what do I have? I have 2 of j sine k omega 0 divided by 2, right? Because cosine and cosine goes away and you have double of sines. Oh, I forgot to have this j here. Excuse me. What is it for the numerator? You do the same thing because you have the same pattern, right? You have minus sign here. If you do the same thing, then you will get 2 times j times sine of k omega 0 and 1 plus 1/2. Therefore, so if we rewrite this equation with this numerator and denominator, then please inform that we just dealt with this parenthesis. So I can say that AK times large N equals the thing that we just discovered, right? Therefore, I can say NAK is like, what's it gonna be? It's gonna, we have this stuff on the bottom and this stuff on the top, and minus j cancels each other, right? So we will have sine of k omega 0 over 2 sine of k omega 0 2, like this. And moreover, I want to get rid of this this omega 0. So I'm gonna use that relationship. I mean, omega 0 equals 2 pi over a period. And there's no problem if I add this case here, right? Therefore, with this additional relation, I can rewrite this equation by I'm gonna use this omega, large omega, to replace this k omega 0, to replace this k omega 0. I mean, I'm gonna use the term omega here for the final representation of this solution. And then I will have sine of 2n1 plus 1 over 2 times this omega, like this. And what should omega be? It should be 2 pi k over n, like this. Okay, so I can have this final representation using this sinusoidal wave. I mean, you can so what does this mean to have k times omega 0 as omega? It means that you can only insert the values which are harmonically related frequency for this omega. So this means you can generate the value omega only by harmonically related frequencies. Okay, so it's a multiple of omega 0, because k should be an integer. Okay, so and you can see that so I think I'm gonna stop here, but I think you can recognize that this AK here is periodic. Okay, in terms of this k here, because you have the periodic signal divided by periodic signal. Therefore, you will have the periodic signal, which was not the thing that happened with the continuous sign. So I think I will call it a day and continue our work next time. I think we have to stop because we ran out of time. Okay, thank you very much for your attention, and I will see you in the next video. If you have any questions, please email me. If I did something wrong during the calculation, please correct me by the email, then I will respond with a new video. Okay, thank you very much, and I'll see you in the next lecture.